Hello there, Mr. Sutton here, bringing you this lesson on FTC integral evaluation with non-polynomials. In this one, we're using the fundamental theorem of calculus to evaluate definite integrals that don't have polynomial functions, and we will also be using the FTC to find function values. We're going to start this one off by trying to take the integral of a rational function. Pause the video based on what you've done with antiderivatives before, and see if you can do this one. All right, so the very first thing I'm going to do, I'm going to rewrite this as 4x to the negative 2, just to make my life a little bit easier with my reverse power rule. Antiderivative, this is going to bump up to a negative 1. Dividing by that, I've got negative 4x to the negative 1, evaluated from negative 4 to negative 2. And now plugging in these numbers, I've got negative 4 times negative 2 to the negative 1, so essentially negative 4 over negative 2. And then I've also got negative 4 over negative 4 that we're subtracting. And simplifying that a little bit here, these negatives cancel. This is just 2. Over here, let's see, this is really just a positive 1 that I'm subtracting. So I'm just doing 2 minus 1, which comes out to 1. Man, who would have thought? Now, one other interesting thing on this problem is, what if my interval had included 0 in it? And why do I ask that? Well, we have a vertical asymptote at 0. So notice I didn't give you a problem that had that in there. But what would we have done if that was an issue? Well, for those of you in BC Calculus, we're going to learn about that later. That's called the idea of an improper integral, or it's one of them. But for now, don't worry about it. You can't take an integral if you have an asymptote in there. So just hope you don't get one of those. Here's another problem with some weird oddball functions. We've got 4 over x and minus sine of x. Now notice that I don't have 0 in my limits, in between my limits of integration. So this is another one where I'm not running into that vertical asymptote issue. But pause the video and see if you can remember how to do these antiderivatives. All right, so for something over x, that's ln is the antiderivative. So this is 4 times the absolute value of x. And now negative sine of x, antiderivative of that's going to be positive cosine of x. And we're going from negative pi to negative pi over 2. So I've got all this stuff with negative pi over 2 plugged in, minus all this stuff with negative pi plugged in. I could keep going if I wanted to. I mean, I can definitely simplify the cosine of negative pi over 2 negative pi. But this will just be our reminder that on the free response, trig and log functions with constants actually don't need to be simplified. They count as constants. Now again, you might need to simplify them on multiple choice, but free response, this would be considered done if you didn't need to do anything else with it. On this next problem, which we're going to use the graphing calculator for, we're trying to evaluate this piecewise function. So this function has a linear rule if you have an x value of less than 2, and then greater than or equal to 2, we're using this quadratic rule. So when we have a piecewise function, there's a couple ways to do this. The most reliable way to do this probably, and you could actually do this without a calculator too, is to split up the integral around whatever your border value is. So have one integral for the first half of this, and then another integral for the other, not half, but the other part of this. So with that in mind, I would set up the integral first, then try it out on the calculator. Pause the video and see how that goes for you. All right, so I'm going to set up two integrals. I'm going to have an integral from 0 to the border value of 2, and that's going to use this first 2x minus 3 piece of the function. And to that, I'm going to add the area that I get from another integral. This integral will go from 2 to the final limit here of integration 3, and that's going to use this quadratic rule. And now it's just a matter of entering all this in the calculator. So let's go to Desmos and do all this and clear out whatever else we have in there. All right, so let me write in my functions. So I've got, well, let me just do the integral. So we've got integral, and I'll move it up here so I can see, from 0 to 2 of 2x minus 3 dx plus integral from 2 to 3 of, and now I need to move it a little more so I can see this other part. We've got x squared minus 2x
and then we had a plus 1 there to go with my dx. And all of that is coming out to 0.333, so 1/3. So this will conclude part 1 in just a moment. Before we truly conclude part 1, though, I did want to show you, if you are able to use a calculator, you actually can set up a piecewise function in the calculator too. So feel free to stick around to see how I do that. So to set up a piecewise function, first off, let's define this as just f of x. So define your function name and then equals, and now you have to open a left curly brace, like this one. And for each rule, the format is you have to put the condition first, followed by a colon, and the actual rule itself. So my first condition is x less than 2. So I'll write in x less than 2, colon, and then what's the rule? 2x minus 3. And now we're going to separate our different branches with a comma. For my next rule, and the space is optional here, I have an interval that's x greater than or equal to 2, so that's the interval, colon, and my rule, we've got x squared minus 2x plus 1, and then close the curly brace. So you can see, if you've done this correctly, that we actually do look at our piecewise function on the graph. We can see it. And if we now go and just try to do the integral of this thing from 0 to 3, so int 0 to 3 of f of x dx, it does give us basically the same answer we got splitting it up. So this is another option, but given that you might not actually remember how to do this kind of under a time pressure, splitting up the integral also works. So that officially concludes part 1. Join us next time when we see how to use the calculator and integrals and fundamental theorem to find some function values.
At this point, we're going to shift gears a little bit and see another way that we can use the fundamental theorem of calculus. So let's say that f prime of t is the rate of change of f. It follows then that the integral of that rate of change is going to be the total change of the function from a to b. If I'm taking all these little tiny changes and adding them up, I get the total change. So keep this in mind because it's going to be an important concept for what follows here. So let's go back to our fundamental theorem of calculus. We said the integral from a to b of f prime of t dt. If I take my antiderivative here, I can write this as just plain old f of b minus f of a. This is just integral evaluation, FTC, nothing new. What's new is, let's say I want to solve for f of b. Well, algebraically, to do that, I just have to add this f of a over to the other side. And then the other thing over there, I'm just adding that to the integral that's already over there. So if I want to solve for the value of a function at a certain point, and I know the value of the function at another point, and I also know the integral of the derivative of that function between those 2 points, then I can come up with my new point here. Just to write it out in words, to find f of b, you're just going to add f of a and the integral of f prime from a to b. Now, you might be wondering, well, why wouldn't I just plug b into my f function? Obviously, this is going to be more useful in situations where you can't just do that.
So now that we've seen the theory of how you can use a defined function value and the rate of change of a function to find new function values using the fundamental theorem, let's see if we can put that theory into practice. Pause the video and try out this one where they give you the value of f of 2 and the function for f prime, and they want to know f of 10. And again, you can use a calculator for this particular problem. All right, let's see how that worked out. So let me get my general setup first. I always have to write down what I'm about to plug into my calculator if I want credit for it. So we have the initial value of f of 2. I'll just say f of 10 equals f of 2 plus I need the integral from 2 to 10 of this f prime. And I can literally just write f prime. I don't have to rewrite this function here because f prime is already defined. So f prime of x dx. Now let me actually enter all this in the calculator. How do we do that? So let's go to Desmos, and in order to actually enter this so that it works correctly, first off, if you try doing something like f of 2, equals 8, it doesn't actually work. So don't do that. Actually use the value of 8 where you have f of 2 here. Also, if you try to define something with f prime, it's also going to be unhappy. So typically you're going to want a different name like g or h or something to represent this derivative function. So we'll call this g of x. We'll just define this equals e to the x minus x exponent negative 4/5. All right, so that's the derivative f prime. Now let me set up what I'm actually doing here. So I'm going to have 8 plus, let's do the integral, int, from 2 to 10 of, and we'll do g of x, because that's what I defined f prime as, g of x dx. And that is coming out to about 22,024.896 if I round all that off. For this next example, they're telling us that g of negative 7 equals negative 6. And they've given us this graph of g prime. They didn't really tell us anything else about the original g function, though. But they want us to write an expression for the g function that involves an integral. And then, after we've done that, we want to find g of 0. So we'll do this in a couple steps. First, we'll get our expression, then we'll plug in 0 to that expression. So when you're writing out your expression for g of x, you can use this idea of initial value plus integral of rate of change. You're going to find that you need two variables in there. You're going to need one variable for your upper limit of integration, because that's what's going to be changing here. You're also going to need a different variable for the integration itself. So you need to use a different variable inside that integral. And it turns out that if you try to use the same variable in your upper limit of integration and as your variable of integration, it will not work. You will lose credit on the AP exam if you're taking it, and also Desmos won't be happy either and will flag you with an error. So make sure you use different variables. T is fine. So with all that said, pause the video and give it a shot just writing this expression first. All right, so I'm going to have g of x equals, and I have my initial value, g of negative 7. And it's up to you whether you write g of negative 7 or just write negative 6, but it's defined, so you can leave it like this for now. Plus, we have an integral from the starting x value, which is negative 7, to whatever x value we want, which is x. And now in here, we're going to have to take the integral of the rate of change of g. That's given by this g prime graph. So I'm going to have integral of g prime, and now I'm going to have to use a different variable other than x. So I'm going to use t. That's typically what we use. But you could use whatever else you wanted. So g prime of t, and then make sure your differential here matches. So this is going to be dt. And this is what a correct version of this function would look like. All right, so using this now, pause the video and see if you can figure out g of 0. So for g of 0, we're going to actually have to plug in the negative 6 for g of negative 7. So we've got g of negative 7. We'll figure that out in a minute. And we're doing integral from negative 7 to 0 of g prime of t dt. So that's going to be negative 6 plus, now to take this integral, I essentially just need the area under the curve from negative 7 to 0, going in that direction, which is important. So first I need this triangle that's under the x-axis. Since I'm going left to right and I'm under the x-axis, this is going to be negative. So we're going to have negative 1/2 times a base of 5 times a height of 1. And now the next piece here, we're above the x-axis, so it's positive. This is basically a quarter circle, so 1/4 times pi times the radius 2 squared. And if this is a free response, you can just actually leave it like this, and that'll be fine and it'll count. But if you need to match with an answer choice, then we would have negative 6. This would be minus 2.5, so negative 8.5 if we add those together. And then over here we have 1/4 times 4 pi, so just plus pi. And that would do it. So this concludes our lesson on the last piece of the fundamental theorem. We are fundamentally done with this one. Until next time, Mr. Sutton signing off.